Okay, so we talked about some stuff yesterday. We summarized, we looked at limits of rational functions as x approached plus or minus infinity, right? And the purpose is we want to know what the end behavior, thank you, what the end behavior of the function is. Does it have horizontal asymptotes or not? We'll talk about some other possibilities today of some things that could happen. So we had some guidelines, right? We said if we have a rational function, remind me, what's the definition of a rational function? A rational function is a ratio of? No. It's a function. So what kinds of, it's a fraction made up of what kinds of functions? What's on the top and the bottom? Say it again. Well, no, I mean they're functions. What kinds of, a rational function is a class of function. It's a fraction, but what's in the numerator and the denominator of a rational function? No. Polynomials. It's a ratio of polynomials. Okay, so if I have a polynomial divided by a polynomial, then we have some guidelines. We know without having to do any work, we know what to expect for our end behavior, right? We said that if the numerator has a lesser degree than the denominator, so the bottom is a weaker polynomial than the top is a weaker polynomial than the bottom, then the limit at plus or minus infinity is 0. So you get a horizontal asymptote at y equals 0. If the degree of the numerator and the denominator are equal, then the limit at plus or minus infinity is the ratio of the leading coefficients. And then if the degree of the numerator is bigger than the degree of the denominator, there is no horizontal asymptote. Something else is happening, right? Rational functions share the same end behavior on the left and the right every time. So there's a single horizontal asymptote that guides the function both on the left and the right, which is convenient. Okay, so here's a way of kind of breaking this down and summarizing it. There are three possibilities. First two are sort of grouped together. The first two possibilities are the ones that do produce horizontal asymptotes. The third possibility does not, right? And here are the outcomes. As x approaches plus or minus infinity, when the top is weak, you get the horizontal asymptote y equals 0. If they're tied, if the degree is the same on the top and the bottom, the horizontal asymptote is the line y equals whatever the fraction is. That's the ratio of the leading coefficients. It's going to be some constant. Okay? Give me 1 to 5 on all that stuff. Is that ringing a bell from yesterday? Okay? All right. Okay. A better way, in my opinion, to do it is not to worry about any of that stuff. It's always just to look at the ratio of the leading terms and see what that gives you, right? Remember what we looked at yesterday? If we have polynomials on the top and the bottom, in the limit as x approaches plus or minus infinity, only the leading term matters. That dominates. So we just look at the ratio of the leading terms, and that gives us a monomial divided by a monomial, and so that's easy to simplify, right? Given that way of thinking, well, this isn't really this isn't a rational function, but what is the end behavior of this function? If I zoom way the heck out, what is this graph going to look like? What, say it again? Well, I mean, constant? Negative 3 over 52 is just a number. Yeah, so it's going to look like that, right? The end behavior would be it's the dominant term, the leading term. The function in the limits as x approaches plus or minus infinity, it's exactly equal to that, the end behavior. It looks exactly like it, okay? It's indistinguishable when you zoom way out. Remember we saw that yesterday? We kind of saw that when we zoomed way out on that polynomial. And if we want to look at this one to prove it, there it is, right? there's the where is that polynomial? There it is. If I zoom way out, there it is. Okay. Looks kind of bizarre. I'm going to have to probably rescale this thing a little bit. But if I keep zooming out, what does it look like? It's eventually going to look like the blue one if I zoom out far enough, right? The red one's the whole polynomial. The blue one is just the leading term. And again, if I just kind of rescale this, now we start to see it, right? If I keep going, you couldn't tell the difference. Okay? So how about this one then? Which power function models the end behavior of this function? When we talk about a power function, remember what a power function is. That's a power function. Anything of the form a times x to the n, where a is a constant, so we have some coefficient times the power of x. Well, what's the power function that's going to model the end behavior of this function? If I want to know what it's doing on large scales, that's all I have to do. Just look at that power function model. What is it?
3x cubed. Would it be over x times 2?
Well, we only have to look at the ratio of the leading terms, right? Because as x approaches infinity, the only terms that matter are those two, right? The rest of it just goes away. So I'll just simplify that. The power function would be equal to 3x cubed over x, which is what? What does that simplify to? 3x squared. Let's check it. See if she's right. Okay, so there's the function, right, that we started with. And there's the power function you guys told me. If I take the ratio of the leading terms and I simplify, do they look the same? Well, they're about to. Yeah, I probably don't have to do this again. There, see, they look the same. They're indistinguishable, right? If I zoom out. Okay, how about that one? What's the power function that models the end behavior of this one? You should all be able to just tell me. 3x cubed? Negative 3x cubed, right? And again, we just get that from there, right? So whatever that power function does, that predicts. And do you guys get what we mean by the end behavior then? What we're going to do here eventually, it's going to be a little while, but eventually we're going to do a section on analysis where we do really in-depth curve sketching. I'm going to give you a function, you're going to do a bunch of calculus, you're going to find the locations of all the extrema, the points of inflection, all that stuff, but included in that is going to be all the asymptotes. The asymptotes form like the skeleton of the graph. Everything kind of sticks to the asymptotes. So knowing the end behavior of the function either gives us asymptotes or it gives us some guiding power function that tells us what the function's going to do way out at the tails when we zoom way out. So that's the large scale behavior of the function. A lot of times we don't care about that. A lot of times we want to know what's going on for smaller values of x. But if we want to know what's happening for very large values of x, so extremely far to the left or the right, These rational functions are very easy to analyze. All you have to do is just look at the power function that guides the end behavior. Okay? Give me 1 to 5. Is that sticking? We getting that? Okay? All right. So what about, let's try something. Let's try sketching this one. Now, sketching a graph is different than graphing it. Sketching a function. Graphing a function is what you do with technology. You don't graph a function on paper because you're going to do a crappy job. It's not ever going to be perfect. But a lot of times we don't care if it's perfect. So we call that a sketch. We just want to know the locations of the interesting features on the graph. Now, we're not really far enough along to find a lot of those interesting features because they rely on calculus. But we could do some interesting stuff. We might be able to find the locations at least of the horizontal and vertical asymptotes and sort of sketch how the function adheres to those asymptotes. How is it going to approach them? So what am I going to do here? If I want to find, being as we're talking about horizontal asymptotes, can you guys tell me does this have horizontal asymptotes? It does not have horizontal asymptotes, and why? You can just look at it and tell. Horizontal asymptotes are the limits at infinity, right? How come that has no horizontal asymptotes? You can just inspect it. You don't have to do any work at all. Just look at it and inspect it and tell me. No, it doesn't.
Well, because the bottom would be 0.
What do you mean the bottom would be 0?
The bottom would equal 0.
What do you mean by that?
Like for there to be talking about horizontal or vertical?
Horizontal.
So for a horizontal asymptote, it has to be a non-zero or a 0.
For a horizontal asymptote, we want to know that for us to get a horizontal asymptote, there's only 2 possibilities. When I take a limit as x approaches plus or minus infinity, I'm either going to get 0 or I'm going to get some other non-zero constant. Right? What were the conditions? When did we get 0 for our answer? Because this is a rational function, polynomial divided by polynomial. What do you think, Sarah Lynn?
When the bottom degree is bigger than the top.
Yeah, when the degree of the bottom of the polynomial is bigger than the degree of the top. And let's think about why that might be. Like, let's look at a quick example where that would be the case. I'm going to make one up. Like, what if we had this? How about, other way around. Okay, if I look at that polynomial as x, if I take a limit as x approaches plus or minus infinity, what's going to happen? Well, both the top and the bottom are going to approach infinity, right? Which one's going to approach infinity faster? The bottom. How much faster? Infinitely faster, right? Because it's a higher, we have an extra product of infinity in there as we're approaching infinity, right? X cubed approaches infinity infinitely faster than x squared does. Right? Agreed? Does that make sense? So if the bottom is approaching infinity infinitely faster than the top is, what's the value of that fraction have to do? As x approaches infinity, it's got to go to 0 because the bottom is going to explode compared to the top. And a big denominator makes a fraction small, right? That's just another way of thinking, of conceptualizing it, right? Okay, so we know that that's what would happen if you had, that's how you get 0. How would you get a constant for your, like a y equals some non-zero constant for a horizontal asymptote for a rational function?
The top and the bottom are the same.
Top and the bottom were the same order, right? Same degree polynomials, in which case they would both go to infinity at the same rate, but it would just which one has a bigger coefficient would determine, right? Does that make sense? So we don't have that either. This time the top is going to infinitely faster than the bottom, and so this is not going to have a horizontal asymptote. It is going to explode to infinity as x goes to infinity, right? So no horizontal asymptotes. Are there any vertical asymptotes? How would we know? What do you think? Sarah Lynn, what do you think? Okay, if there's a value of x, if there's a unique zero of the denominator, right? There's a value of x that makes the bottom zero but not the top, then that's guaranteed to give us a vertical asymptote. So what answer is that going to be here? What value of x produces a unique zero of the denominator? 2 minus does not. If I take this limit as x approaches -2, what does the bottom become? -4. That's okay. That's not 0. What's the only value of x that makes the bottom 0 but not the top? 2. Yeah, right? Okay, because if I evaluate that directly, I get 0 on the bottom. What do I get on the top if x approaches 2? 24 minus 21, is that right? So 3? That seem right? What result is that? Well, I get a non-zero number divided by 0, so I know I get a vertical asymptote. If I were going to sketch this guy, I know I've got a vertical asymptote at 2. Okay? I don't know much about this thing, but I know that. How could I, if I wanted to make a sketch of this, how could I determine what's happening as we approach that asymptote from the left? What kind of a limit would I need to take if I want to know what's the function doing as it pushes up against that asymptote? As x approaches 2 from the left. Okay? So let's see what we get if we do that. What do I get? What do I get on top? 3. Because I'm approaching 2. And I already know what that is. On the top, I'm approaching a value of 3. Whether it's slightly less than 3 or slightly more than 3, who cares? It's 3-ish, right? It's a positive constant number. What do I get on the bottom, however? If I'm approaching 2 from the left, what's 2 minus subtract 2? Everybody agree that's 0 minus? I have a number slightly less than 2 minus 2 gives us a small negative number. So what's the answer? Okay, negative infinity. So we know from the left side, we're doing something like that. Okay, from the right side, what limit would I take? 2 positive, yeah. And what are we going to get? If we'll call this f of x. The limit of f of x as x approaches 2 from the right is going to be 3 on the top. That's not changing, right? What's the bottom going to be? 0 plus, so what's the result? Okay, so on the right side, we're doing something like that. And there is no horizontal asymptote, so we can't really draw a horizontal asymptote. There may be some, oops, I put that in the wrong spot, didn't I? There may be some interesting behavior that's happening in here that's obscured for us right now because we don't know how to do calculus. But later on, we'll be able to use calculus to be able to see if we have some peaks and valleys and interesting stuff like that going on. But for now, we don't know. Okay, but we do know one other thing, at least slightly helpful. What is the end behavior of this function? So as x is approaching plus or minus infinity, this whole thing is equal to the limit of what? Greatly simplified function. If I want to explore end behavior, what's our great trick here? I know there's no horizontal asymptote, but can you tell me the function that does guide the end behavior? 3x squared. How come? You're right. Somebody else explain that to me. Why? How do we get 3x squared? How do we get it? Leading terms, right? Because as x approaches positive or negative infinity, what are the dominant terms in any polynomial? The leading terms. So all we have to do is look at the leading terms on the top and the bottom, look at that ratio, and that's going to tell us what the power function the power function model of the end behavior is going to be. So the end behavior is going to look like 3x squared. What's the shape of that? That's a parabola. Yeah, so I know, right. So I know that if I were to go clear out to the ends, I know that this thing's going to eventually do that kind of stuff at the end. So I got a pretty good idea what's going on with this function. I just don't really know the locations of all the interesting stuff that's happening in here. I just know the vertical asymptote and the end behavior. And if we want to just see what's really there, okay, there it is. So it worked, right? Let me spread that out just a little bit. Let's go. Okay, does that make sense? We were right, weren't we? We said the vertical asymptote was at 2. Well, there it is. The blue line's the vertical asymptote. We got that. And if we want to look at the end behavior, we said it was going to be similar to that guy. I'll make it green, how about? So we could say that that's the envelope of the function. Is another way of describing that. That green parabola describes the end behavior, models the end behavior. Okay, give me thumbs. Is that making sense? Okay. So this is in math what we call analysis. How about this one? All horizontal and vertical asymptotes. We got sine. Is that going to be problem? Okay, now the sine is definitely going to impact the way this thing looks, but I'm not really asking you for what it looks like. All I want to know about are horizontal and vertical asymptotes. So first of all, let's do the horizontal asymptotes because we've already got that limit set up. We're approaching positive or negative infinity. What's the answer going to be? Yep.
Does the x squared in the sine function affect it at all?
Well, you tell me. Is that going to be a sine function? How is the size of that sine? Look, we got two terms in the top. We've got the 6x minus the sine of x squared. As x is approaching infinity, how's the sine x squared, the sine of x squared, going to compare to the 6x as x approaches infinity, the sizes of those two terms? What can you tell me about the magnitude of sine x squared? Yeah, it's always between 1 and negative 1, so who cares? That's insignificant. 6x is going to grow, as x gets really, really big, 6x is going to get huge. Sine x squared is always going to be small, right? So we can ignore that term, can't we? As x goes to infinity, because that's a contained term, right? It's constrained to be between negative 1 and 1. So even though the point I want to make with this one here is that even though, thumbs up or down, is that a rational function? Is this function up here that we're taking a limit of, is it a rational function? You guys already defined a rational function. It's a ratio of polynomials. Well, is that a polynomial on the top? No. Polynomials just have real number coefficients times powers of x, right? Where the exponents are whole numbers, right? So 3x, does that make sense? Thinking back to what polynomials are? So that is not a polynomial because I've got a sine function there. Sine's not a part of a polynomial. So it's not a rational function, but we can treat it like a rational function when we're looking at end behavior because that sine x squared term is extinguished. When x gets really big, that just becomes insignificant, right? And so we still, if we're looking at the large scale behavior, does it make sense that we can still just do something like that? Because those are the terms that are going to grow without bound, and the other terms are going to be background noise. They're going to fall away. Give me up, down, sideways on that. Does that make sense how we can treat it that way? Okay. See if somebody can ask a question to clarify. Yeah, I'll tell you what, let's look at a graph. Let's look at a graph. Picture's worth 1,000 words, right? We'll look at a graph. Okay, there it is. Why is it so wiggly? Because there's a sine function in there, right? I tell you what, let's just look at the graph of the top. I'll turn that one off. There's 6x minus sine x squared. Yeah. Do you even see that it's wiggly? I mean, you can kind of see it a little bit, I guess, but I mean, it's a little bit wiggly. That's what the sine function does, okay? But ultimately, what is that graph going to look like if I zoom out? Just the purple one, 6x minus sine of x squared. It's going to look like 6x, right? Because the 6x, as x gets really big, 6x is going to be huge, sine x squared is going to be tiny, right? So if we graph y equals 6x, well, look at that. Let's make that orange. I mean, you can't tell any difference, right? The sine x doesn't contribute when x is really big. Okay? Make sense? Okay. Okay, so we know that the limit as x approaches plus or minus infinity is just equal to the limit of 6x over 2x, just the ratio of the leading terms, which is 3, right? So what's the equation of our horizontal asymptote for this thing? Y equals 3. Yeah. Right? So we know that much. If we're going to make a graph of this, so there's our horizontal asymptote. There's the line y equals 3. When we graph this thing, I guarantee it's going to stick to that when we go far to the left or the right. Yep.
Can there be more than one horizontal and vertical?
Yeah, it can be lots of vertical asymptotes. Any unique zero of the denominator produces a vertical asymptote. So if the denominator had a whole bunch of factors and numerous factors in the denominator were zeros of the denominator, right? Numerous values of x were zeros of the denominator, but not the numerator. Each of those would give you a vertical asymptote. So you can have as many vertical asymptotes as you want if you want a complicated enough function, right? Horizontal asymptotes, the most you could have is how many? Well, you can have one for sure. Could you? Two. You're right. How come? Well, I mean, think about it. What is a horizontal asymptote? Horizontal asymptotes are the limits as x approaches positive infinity and negative infinity. Now, you might have none. They might be the same horizontal asymptotes to the right and the left, in which case you'd only have one, or they potentially could be different. You could have one horizontal asymptote on the left and one on the right. We haven't looked at any functions like that yet, but we will. Okay? So the most you could ever have, most horizontal asymptotes would be different ones on the left and right, which makes two. Okay? All right, what about vertical asymptotes? Are there any vertical asymptotes here? Okay, I want you guys to answer that for me. Give me thumbs up or down. There is a vertical asymptote. Yes, thumbs up or down. Yes or no? Katie, you gave me thumbs up. What's your thinking, and what do you think it is?
If you substitute 1, wait, no, it would be -1 to the denominator to get 0 down there, but not 0.
There you go. Okay, there is 1 0 of the denominator. If I set the denominator equal to 0 and solve, the only 0 of the denominator is -1, correct? All we have to do is ask ourselves, if we want to determine if that's a vertical asymptote, is ask, is that a 0 of the top? Well, if I plug -1 into the top, I am guaranteed not to get 0, right? Because if I plug it in, -1 times 6 is -6 minus the output of sine can only swing between -1 and 1, so that could never drive the top to 0, right? Because the first term equals -6, okay? So yes, we are guaranteed to have a vertical asymptote at -1. So we already know a bunch of stuff, don't we? So we know all that stuff. And that's really all we know. I mean, we could analyze, we could take the limits as x approaches 1 from the left or the right to determine how this thing, where is it being pushed, to positive infinity or negative infinity from the left or the right. You guys get that when a function bumps up against a vertical asymptote, it always has to get diverted either to positive infinity or negative infinity. And the one-sided limit will always tell you which one. Okay? That makes sense? Okay, so let's look at that. So let's look at that. Let's figure out what it's doing when the function bumps into our purple vertical asymptote from the left. We want to know, is it getting bumped up or down? So all we'd have to do then, we'll make that our green limit. We're going to take the limit of this function, 6x minus sine of x squared. And let's factor the bottom. Let's make that 2 times the quantity x plus 1. And let's approach -1 from the left. If I approach -1 from the left, what outcome is that going to give us? On the top, I'm just going to get like -6, I'm going to get a negative number. Agreed? I'm going to get a negative number. It's going to be -6 plus or minus some value between 1 and -1. Agreed? Because we don't really want to figure out what's the point of, we could plug this in a calculator and get a decimal answer, but we don't really care. We just know it's going to be some negative number. Right? On the bottom, what are we going to get? We're going to get 2 times, as x approaches -1 from the left, what's that going to look like? What's a number slightly less than -1, like -1.0001 plus 1? That's 0 minus times 2. What's 0 minus times 2? 0 minus. So I'm going to get a negative positive, I'm going to get a negative finite number, I'm just going to call it a regular number, 5 point something, right? Divided by 0 minus is what? It's going to be infinity. I know that I've got a macroscopic number on the top and a number approaching 0 on the bottom, so I know I'm getting infinity. Negative divided by negative is positive, so I know that this thing is doing that from the left. It's getting bumped up to positive infinity. Yes. Yeah.
Also, does the negative in front of the sign, does that mean anything?
Does this mean anything?
Yeah.
Yeah, that we're subtracting that term.
Yeah, but for the part where you plugged in the negative sign.
Well, it does, but so when I plug in -1, does anybody know what -1 squared is 1, right? Anybody know what the sign of 1 is? I don't. Sign of 1 is just think where 1 is on the unit circle. On the unit circle, there's pi halves, which is like 1 point, like half of pi. So it's like what, 1 point, something weird like that, right? So 1.56 or something like that, right? So 1's going to be like right about there somewhere. The sign is going to be some number slightly less than 1. Whatever it is, we would just plug that in and subtract it from -6, and I'd get like -6.8-ish. But it doesn't really matter because I just know I'm going to get some negative number on the top and a 0 on the bottom, which drives it to infinity. Okay? Okay? All right, so now let's look at, I want to remind you about something. When are we out here, 45? Yeah. Okay, so this will be a good thing to end on for today. And then we'll come back and we'll just to be continued on Monday. So let's analyze the behavior of the absolute value of x. This is a really important function for us in math. And you've seen all this. I know we did a bunch of this a couple years ago. We always want to break that into a piecewise function. Okay, the absolute value of x has really 3 pieces, but really the middle one is just a boundary. How do we define the absolute value of x as a piecewise function? For positive values of x, what is the absolute value of x equal to? X. Yeah. It's equal to x. For negative values of x, what is the absolute value of x equal to? No. Negative x. Well, okay, but the absolute value of x is equal to the opposite of x when x is negative. If I input a -7, isn't the output +7? So it's the opposite of -7, right? If x is the input value, if the input value is negative, to make it positive, I have to multiply by negative, right? -1. And if x is 0, obviously the absolute value is 0, right? Okay, so then what is the absolute value, if I take a new function, the absolute value of x divided by x? What would I get? Well, when x is greater than 0, I would just end up with x over x, right? Which is what? Which is 1. Okay, so that whole thing is just going to simplify to 1. Okay? When x is negative, I'm going to get negative x over x, which is going to simplify to -1. And in the middle, it's got to be undefined because I can't divide by 0. Right? So this function is undefined. 0 is not in its domain. Okay, is everybody following this? You got to really focus on this to get this. Oops, I don't want to do. I don't know what that was. Okay, so we would just say that, right? We could simplify it and say it's equal to 1 whenever x is positive and -1 whenever x is negative, right? So it looks like that. The absolute value of x over x looks like this step function that has, so now we see an example of a function that it has, I mean, technically that is an asymptote, even though it's actually the function, right? It's split, so it's got different infinite behavior on the left and on the right, okay? Everybody see that? Hold that thought. We're going to use that on Monday. Okay, there is an assignment up there that you could, I broke it into 2 pieces. Today's kind of like the intro piece, and so the assignment, you could jump in and do some stuff. After Monday, you could do the rest of it, the part 2.
Infinite functions.